begin by talking about the so-called y simple region. So in y simple region, x is bounded by 2 points, so A and B. And y is bounded by a lower function and an upper function. Okay? So y is bounded by a lower function g1 of x. So I have a function g1 of x. And have another function g2 of x. So one function is in below, the other function is above. So this I usually call a lower function. So this is what I usually call the upper function. And the region is bounded by 2 vertical lines and 2 curves given by 2 functions. This will be the y simple region. Okay? So this y simple region is a more generalized region than the rectangles. All right? So in the rectangles, I can indeed regard this as a y simple region as well. So the only thing I need to identify a region as a y simple region, I need 2 points for x, 2 functions for y. Okay, keep in mind, this is the number one thing you have to identify a y simple region. I need 2 points for x. So if I'm looking at this rectangle, I have 2 points for x. I also need 2 functions for y in order to identify it as a y simple region. So the lower function is a constant function g1x equals c. The upper function is also a constant function g2x equals d. So this is also a y simple region. Okay? But the general y simple region is much more general than a rectangle. Okay, so this is the first step. You have to be able to identify a region as a y simple region. You need 2 numbers for x, 2 functions for y, and then I can write down the double integral with respect to y first. Okay? So as long as you identify a region as a y simple region, you need to write down your double integral in this particular form. Y has to go inside, x has to go outside. Okay, x has to go outside for a very natural reason. Because after you eliminate all the variables, you're supposed to get a number. Right? You're supposed to get a number. So if I have these functions in the outside, there's no way I can get a number. Okay? So if it is a y simple region, you need to integrate with respect to y first. This is a y simple. And this is essentially why it is called a y simple region. It means you want to do y integration first. Okay? So I will give you a very simple example to begin our discussion. So from 0 to 1, x cubed 2x, xy, dy, dx. Okay? So 2 things I want to mention here. 2 things I want to mention here. First thing is, as long as I give you a double integral to evaluate, you can start your evaluation without caring about what the integrating region is at all. You can just start doing your single variable calculus immediately, regardless. You know with me? I don't have to care about what a region like. I don't have to care about whether it's a y simple region or x simple region. I just look at this double integral. I evaluate the interior integration with respect to y, and then going outside eliminate x. You know with me? That's the first thing. You can always do your double integral, regardless. So if I do that, so from 0 to 1, I'm finding the antiderivative xy with respect to y. What is it? Half of xy squared. And then, as I said last class, when I eliminate the y variable in the interior integral, I really keep the evaluation clear here. So I want to evaluate from y equals x cubed to y equals 2x then dx. Okay? And then, so the function I need to evaluate is half of x, y is equal to x cubed. So this is x cubed to the squared minus half of x multiplied by 2x squared dx. All right? Again, I can verify Questions? Again, I can.
Isn't it
Isn't it
the
the
other
other
way
way
around?
around?
The other way?
Yeah.
Shouldn't it be 2x?
Oh, yeah, thank you. So
Yeah.
I'm supposed to go the other way. So this is supposed to be 2x, this is x cubed. Thank you. Again, I can verify after I eliminate the interior integral, I'm supposed to have a function involving x only. All right, there should be no y appearing here at all.
So do squared.
Squared.
The first term?
Squared. So I'm getting from 0 to 1. So it's 4x squared, so it's going to be 2x to 5 minus half of x to 7 dx. And then you can find the number right here. So it's going to be x6 divided by 3 minus.
Professor, it's x cubed. Instead of, it's 2x cubed instead of 2x to the fifth.
Am I making any mistake? This
Yeah.
one? Oh, okay. So I have x squared, so it's x3.
Yeah.
Right? So it should be x3, thank you. So that's why I'm having x to 4 divided by 2. Right? x4 divided by 2. So that's why when I take the derivative, I plot 4 and I get 2x cubed. And this one is x to 8 divided by
16.
16.
Yeah.
Okay? And then I evaluate from 0 to 1. Okay? And if you want to make your computation even more clear, it's x equals 0 to x equals 1. So in the end, I have 1/2 minus 1/16. So it's going to be equal to 7 over 16. Okay? So double integral, in the end, it is always a number. Okay? So if you want to figure out what this number actually represents, you can go back to the sign and volume explanation over there. You have a region in xy plane, you have a surface defined by z is equal to fxy, which is equal to x times y, right? And then this number is the volume under the surface above the interregional region, okay? So this is the one thing I talked about before we actually did this problem. The whole evaluation, you don't have to care about what the region looks like, right? You actually didn't know what the region looked like at all. You can still get a number in the end. However, it is very helpful for you to know what the region looks like, where it is, especially if we have to go forward to introduce the x input region, and also we will interchange the intervening order within the x region and the y input region as well. So it will be much more helpful for us to actually see where this region is. Okay? So again, as long as y goes inside, I immediately know this is y simple region. So I needed two numbers for x from 0 to 1. All right? So I needed two numbers for x and two functions for y. The lower function is y equals x cubed. The upper function is y equals 2x. So I have a 2x right here. So this is going to be my upper function. And the lower function is x cubed. So this is the one. So this is the y equals x cubed. Your curves do not have to be extremely precise. The curves do not have to be extremely precise. But it have to be helpful for you to identify the region. So this region is bounded by two numbers, and lower function and upper function. Always be clear which function is lower, which function is upper. So this function is the lower function, this function is the upper function. So the region should be bounded between these two curves. All right? So this is the interregional region. Questions? Okay. Again, I can convince myself this is the y simple region because this region is bounded by two vertical lines, x equals 0 and x equals 1. So this is 0, and it is bounded by two curves, y equals 2x and y equals x cubed. Okay? So as long as we can identify this region as a y simple region and you write down the double integral, the following work will be nothing but two single calculus integration. So the key thing is to identify the region if the region is not written down explicitly. For example, so I want to simply write down the interbreeding region. So the interbreeding region. Of BA is disk radius 4 in the first. I'm not sure I'm spelling this word correctly.
Or the D and the R switch.
Yeah. Okay, so this problem, I didn't really ask you to evaluate a particular double integral. I just want to identify the region. In terms of identifying the region, I want to write down it in this form. I want to write down this in this form. So this region is not written down explicitly, but I know where it is. It is a disk with radius 4, centered at 0, 0, centered at the origin. And also it is restricted in the first coordinates. Okay? So basically this is going to be a quarter of a whole disk. All right? So if I have a disk with center at the origin radius 4, this is going to be my interbreeding region. Okay? So I can easily find this is 0, this is 4, and so on. So I want to write down this double integral in y simple form. Okay? I want to write down this double integral in y simple form, which means I need two numbers for x, two functions for y. So two numbers for x is going to be the left number and the right number, which you can easily find them out, right? So x equals 0 is the left, x equals 4 is the right. So 0 to 4 is x. In other words, this region is bounded by 0 and 4. And then I need a lower curve and upper curve. Lower curve and upper curve are all about the y direction, all right? So this region in the y direction, the lowest you can go is the x-axis, all right? So the lowest you can go is the x-axis. So the lower function I can find is going to be y is greater than equal to 0. X-axis is defined by y equals 0. And the highest I can go cannot go beyond this arc, all right? So this arc is going to be the curve for my upper function, all right? This is going to be the function for the upper restriction. So the upper restriction right here is going to be defined by the boundary of a disk, which is a circle, all right? So this is a piece of a circle. The equation is given by x squared plus y squared is equal to 4 squared, all right? 4 squared. So this is the equation for the whole circle. This is the equation for the whole circle. And because I have restricted in the first quadrant, I needed to solve for y within this quadrant. Are you with me? I need two numbers for x, two functions for y. In other words, I need to solve for y right here. All right? And to solve for y right here. So y is going to be bounded by, solving for y is going to be square root of 16 minus x squared. All right? So solving for y within this equation, I need to divide both sides by, I need to subtract both sides by x squared and then taking the square root. And I'm taking the positive square root because y is positive in the first quadrant, all right? That's why I have this restriction as well. So y is bounded between the lower function y equals 0 and the upper function y equals square root of 16 minus x squared. So I can rewrite this in the double integral dy inside and dx outside. It is a y simple region. And then I can do the following. As I said, the double integral and the triple integral, the most difficult step is to identify the intermediate region. As long as you can do that, regardless of what function you have inside, you're going to do exactly as what we did over there. You eliminate the inside integral by eliminating the variable y, and then you go outside and take the integral with respect to x, regardless of what function you have right here. Okay? So I want to give you one more example so we can, maybe I should erase this one so I can compare all the types of regions. So this region is in this form. Is a triangle with vertices zero, 0, 4, and 4, 8. Okay. So I want to identify this region as a y-simple region. And the region is a triangle with vertices 0, 0, which is at the origin, 0, 4, which is at the y-axis right here, and 4, 8. So it's going to be right here. Oh, no, that's not. That's 4. So this is the one. So 0, 4, and this is 4, this is 8. So the triangle is right here. Okay? Triangle is right here. So this is going to be 4, 8. So again, if I want to rewrite it in terms of x simple region, I'm sorry, y simple region, I need two numbers for x and two functions for y, right? So the x numbers are pretty straightforward here. X has to be bounded between 0 and 4. So x is bounded between 0 and 4. I need two functions